This is the instructional video for the Optical Tweezers lab. So the learning outcomes for this lab are that students will build comfort in developing data and observations which have an unknown outcome. This might seem like an odd learning outcome, but becoming familiar and comfortable with uncertainty is actually really important and something that you don't have much chance to experience. Also, a learning outcome is to gain familiarity with optical research equipment. The lab objectives are basically two things, even though this is written as four things. First, the specific objective is to record several videos that are your form of data of the following things: spherical particles exhibiting Brownian motion freely without any laser trapping, then trapped spherical particles, then trapped and rotating calcite crystals. With that data, as you take that data, you'll measure the minimum laser power needed to trap dielectric milk particles. And after taking the data, you'll analyze the recordings of the rotating calcite to determine the relationship between the crystal axes and the laser polarization. The objective related to the spherical particles is to analyze the recording of the Brownian motion and use that to measure random motion and calculate Avogadro's number from those measurements. So we're going to start with a background on optics. Optics is basically using lasers. So we need to know what lasers stands for, or laser, and it stands for light amplification by the stimulated emission of radiation. So there's laser. Now, lasers were invented in 1958 as the optical maser. I highly recommend looking into all of this at your own pace, your own leisure. It's very interesting stuff. All right, so if that's a laser, well, the things that we care about are that our lasers that we'll be using are monochromatic. That means they have one color. So our laser is red, and specifically it's 660 nanometers. The laser is collimated, which means it travels as a beam that does not diverge or converge. So it would look kind of like a column. Our laser has a defined mode. In this case, it's a Gaussian mode that would look like that front view. And our laser is polarized, which means it has a defined electric field direction. And a brief intro to polarization. This is a linearly polarized wave and a circularly polarized wave. And what you notice is that what this is plotting is the electric field direction. So here, the electric field direction is along this red y-axis, and it would be polarized vertically along the y-axis. Here, the electric field travels in a circle, so follow the tip of that black arrow, which is the electric field. It travels in a circle because the x and the y components are out of phase with each other. And that's called circularly polarized light. We'll be dealing with both linearly polarized and circularly polarized light in this lab. All right, so when we start talking about optical trapping, we want to get a sense of size. Kinds of sizes we're dealing with are 1 micron to 10 microns, and you can see that they're on the order of somewhere around small bacteria to red blood cells, and definitely smaller than a hand or a human hair, things like that. All right, so how does optical tweezers work? Well, the basic idea is that light has momentum. We quantize momentum p as h bar k. And we can think of the momentum of light as being like little balls of light that have momentum in some particular direction. That's particularly important, the direction of those red arrows. If light has momentum, then light can exert force. If momentum changes, then there's a change in force, in momentum with time, and that gives us a force. One type of force is called the scattering force, which is how when light bounces off of an object, it actually exerts a change in momentum. That change in momentum of the light bouncing off the object is transferred to the object itself, and that's what we call the scattering force. You can visualize it like this, where if you shoot a a ball out of a laser or a cannon, and it hits an object, the object moves and as the ball bounces off. And one of our favorite demos is to show a combination of the scattering force and heating in a symbol. All right, so if light has momentum, then when photons change direction, they exert a force. So let's examine how photons change direction as they travel through something spherical. Imagine a photon that has an initial momentum in this direction. It bends as it travels into a different dielectric medium. We assume that the medium of the sphere is higher. The index of refraction is greater than the index of refraction of the surrounding medium. And so it bends. And then when it leaves this sphere, it will again change direction. So look at that. We've got a changing momentum, which means the momentum change is in the direction of this arrow. That means there's a force on our object in the opposite direction. In other words, conservation of momentum. If there's a change in momentum one way due to the object on the light, there's an opposite change in momentum from the light on the object. When we look at our optical focused laser beam, this is what's happening. The photons closer to the center of the beam are more intense, and so they bend in the way that we drew in the picture on the left, and there'll be some force like this large green arrow in this general direction. Well, the photons from near the edge of the beam are less intense. There are fewer of them, and they bend in the opposite direction, but they exert less force. The net force is then towards the center of the beam, and our object will end up trapped in the center of the beam. So that's the basic idea of what we call the gradient force, where there's a net force on the object towards the highest intensity of the beam. This happens when there is a gradient in intensity. That's why it's called a gradient force, or a gradient in irradiance, same word. Okay, so our gradient force means that the particles move to the highest intensity part of the beam. Well, that's either the center of the beam, like we showed here, or towards the focus. So if they're above the focus, they'll be pulled down towards the focus. If they're below the focus, they'll be pushed up towards the focus of the beam. And you can trap objects in the center of the focus of a laser beam. All right, so when we look at our optical tweezer setup, the basic idea of the setup that you'll be working with is that you start with a laser. It's then focused before the microscope objective. It focuses and re-expands. It's actually expanding as it reaches the microscope objective. And then it's focused very tightly into a sample. This high numerical aperture makes a very strong gradient, and that's why you use a high numerical aperture for optical trapping, so that it traps very tightly. Focuses into the sample, and we are either forgetting about the rest of that red light, or we collect it and use it for other things. Above the sample, we have a white light source, drawn here in yellow, and that white light source is focused through our sample and then travels through a two-color mirror and is reflected and refocused, re-imaged onto a camera. So we image our sample region onto our camera, and that's the video, that's the information we'll record. In the sample region itself, we have a cover slip on the bottom, and then our sample region and a glass slide on the top. Right, so one more thing we need to discuss in this pre-lab video is spin angular momentum. Spin angular momentum comes from circularly polarized light, and it was first demonstrated in 1936. Amazing that we could do that at that time. The apparatus looks really different, but you know, it's still a diagram. Things are still labeled. There's a lamp, there's some other things labeled in here, some dotted lines. Think about that when you draw your own diagrams or use pictures. Everything's got to have a label. Okay, the schematic is that as we have light with negative h-bar spin, and then if it goes through an object and gets spin and comes out with positive h-bar spin, it will impart a total spin of 2 bar to that object. Same idea as changing momentum. It is a change of momentum, imparts a linear force on an object. In this case, we impart a torque on an object because of the change in angular momentum. Birefringent objects like this is actually a piece of aragonite that we grew in the lab, not recently. Birefringent objects then rotate because they change the circular polarization of light. They change the angular momentum of light passing through them, and that makes them rotate. All right, so the equipment that you'll be using is from our optical trapping lab, and you'll see a lot of different things happening potentially in the lab. You will hopefully see some of this, mostly the center bit, this one over here showing a trapped biological object. Your systems will be a bit different looking, but you will get used to what things look like when they're trapped in our optical trapping equipment. Okay, so this is the sample prep part of the optical tweezers experiment. You can use this technique for prepping any kind of sample. We're going to prep a little sample of milk, which is one of our colloidal systems. So first, find a clean glass slide. It's okay if it's actually not terribly clean. For what we're doing right now, we will, if something looks terrible, you'll know. Okay, so we're going to place this clean glass slide on our piece of paper, which is marked so that you can see where the center of it is. That just makes things a little more convenient. And the next thing we're going to do is make a sample region. We want a little space to hold a small amount of fluid. And it turns out that double-sided tape is fidgety to work with, but is about 100 microns thick. I don't like that piece of tape, so I'm going to throw it away. Take another little piece of tape. It's about 100 microns thick, and what I want to do is make a small sample region out of my double-sided tape. So first, I'm going to use an extra slide to cut out a small piece of tape. This is probably one of the most awkward parts. You'll need a razor blade, and I'm going to cut a fairly small square out of my tape, being sure to overcut each edge. If there are any edges that aren't fully cut, it will tear as you pull it off. Okay, so I've got my square of tape cut. I'm going to now use the razor blade on one side and my fingers on the other side to gently lift this off of the prep slide. So now I have a small piece of tape with a hole in it. This tape with the hole in it is going to be centered right above my X. That's so that every time you put your sample into the sample region, it'll be in the same place. Now I find it hard to see on the white, so I'm going to shift this onto black. What I want to do now is not put my finger right in that open space, but I am pressing the tape down just around it. Okay, so now I'm ready to put my solution in. You'll either be using milk as a colloidal system, suspension system, or another small container of your calcite solution. So you want to have ready a cover slip, your solution, and something that you're using to get the solution onto the slide. We will probably be using these plastic droppers because they're just fine. So I'm going to take a small amount out of this vial and then drop. I will overfill my little square, drop that on to my sample, close the vial. All right. So now I have a little open square with a drop of solution in it. Take a cover slip, and this is what I call the press and drop technique. I put one side of the cover slip, press gently, and then let go. I might want to dab at the extra solution here that's coming out. And I just press down for, 10, 15 seconds or so. This prepped quite nicely. I have a sample region inside my glass slide here. You can see the milk on the inside. Okay, so the last thing that I need to do is to get the slide ready to go into our inverted microscope, which is our optical tweezers apparatus. This is immersion oil that we acquired when the geology department was moving. I'm going to drop a little bit of this oil onto the cover slip, right in the center where my sample is. And I need that in order to make a good image on my sample region. I'll leave the immersion oil right there. So now our slide is completely prepped and we're ready to take it into the lab. Welcome to Optical Tweezers. This is the first view of the optical tweezers setups. There are two setups in this lab. Optical tweezers setup A is here. Optical tweezers setup B is here. Each has the same laser source, and each has a laser that turns a corner and goes through some optics on the way to the optical tweezer setup. That's the biggest overview of the optical tweezer setup. Each setup has a computer also. And next we'll look at how to physically set the sample into the optical tweezers setup. Now we're going to set the optical tweezers experiment. The first thing you want to do is to check your laser and see what power you're running at. So I'm going to walk over to the other side. My laser is coming out here. There's a power meter that you can move around. Just slide it into your beam. Right now, I'm at about 13 milliwatts. So I'm reading the power meter. I'll write that in my notebook, 13 milliwatts. Slide the power meter out. Okay, so the first thing we need to do is one of the trickiest things. We need to put our sample into our trap. You will have help doing this, so watch the video and then ask for help. So I've placed my sample slide that we made in the other room. First thing I'm going to do is flip it upside down. I want the cover slip on the bottom. Okay, so now this is the awkward part. I'm going to place my sample slide into these hinges. It's always fun watching somebody else do that. Not really. It's actually not very fun watching somebody else do it. Now I'll press it back against the back of the hinges and roughly center. Okay. So at this point, I'm ready to lower my sample. But the first thing I want to do, maybe even before I put my sample in, is figure out what these knobs do. One of these moves the slide forward in this direction. The other moves the slide in this direction. And this one moves the slide up and down. So get a feel, or write down, which way moves the slide down, which way moves it up. Right now I'm turning the knob counterclockwise, and I'm lowering the slide down. As I get close, I turn and look at the computer where I'm watching the sample approach the surface. And there it is. I've got my sample slide against the surface of I can see my milk sample. I have a few things I can do down here, but basically I want to position my milk sample so that I'm trapping objects, trapping little milk balls up against the top of our sample region. You can see on the computer that there's a bunch of objects right in the middle. See where the light is? Filter out that scattered light, reflected light, and I can see my clump of milk globules. If I block the light, they will separate. If I unblock the light, they will clump again. And that shows that they are being trapped in the center of the focus light. Go through the pre-lab questions based on this video and also articles that are posted in the research articles section on Blackboard, and we will be ready for lab.